All right, for our third installment on interrupts, we're going to look at enabling a peripheral interrupt within the Kinetis KL2 series device that is on the Freedom board. Excuse me. So in the last video, we discussed how to enable a systic interrupt. But systic is kind of special. And why was systic special? That the systic was part of the ARM Cortex core, so the M0 Plus core. So when Freescale designed this chip, they didn't necessarily design this core. They got the IP from ARM, and that was just part of, the design package. But what Freescale does is takes the ARM core and then adds other neat stuff in the package. For example, communication interfaces, timers, analog digital converters to come up with a microcontroller. So what we're going to look at is an example of an interrupt that comes from one of these peripherals, because it's a little bit different. It's not hard. It's really only one extra line of code to get it set up. But it takes a little bit of explaining. So for this example, the easiest probably example to look at is one of the timers. So we're going to look at one of the timers once again of how we get an interrupt out of a timer, and then you can use that example that, let's say, if you wanted to get an interrupt out of the UART or whatnot, the same kind of theory applies. So the first manual that is kind of useful to have is the Cortex M0 Devices Generic User Guide. So this kind of provides a very high level, view of the Cortex M0 and kind of the stuff that's in it. Now, one thing that's important to understand is kind of its exception or interrupt model. So if we come down through the exception model here, it kind of lists out the different exception types. Like, for example, reset, a non-maskable interrupt, a hard fault. This is stuff that happens inside the core that it's not happy about. So systic is one of those exceptions. It's internal to the core. Now, there are other interrupts that can come in, but they kind of exist outside of the core, and they're called interrupt IRQ. Now, in the ARM Cortex world, every exception or interrupt gets a number. And so the first 16 are used for internal stuff, stuff internal to the Cortex core. For example, reset, hard fault. Exception numbers, or what we're going to see later is vector numbers, 16 and above, are to be implemented by the microcontroller vendor. So Freescale, TI, Atmel, so on and so forth. So that's the first important distinction, is that the first 16 exception numbers are internal to the core. 16 and above are peripherals outside of the core. And you can read down through here, but in the introduction video, introduction to interrupts, I kind of mentioned this concept of an interrupt vector table. And all this table is on the ARM Cortex. It exists in either flash or RAM. At reset, the vector table starts at address 0. And what it does, it just contains addresses and for vectors. Now, the first address isn't really an address of a function. It's the address of a stack pointer. But after that comes reset, all the way up to, interrupt 15. Now, you notice the IRQ number. They have this thing called IRQ number. They assign negative values. That's just to kind of indicate that that's internal to the chip. But then they also have this thing called exception number or vector number. So starting at the peripheral exceptions, IRQ numbers are simply 16 less than exception numbers to kind of differentiate what's a peripheral. Now, in here it just says IRQ 0, 1. in this document, it's only documenting the core. It's up to the vendor to kind of make these assignments, and we'll look at that, in a minute. So systic is internal to the core is 15. Everything else is above that. So keep in mind we have these IRQ numbers and vector numbers. Vector numbers are kind of used to index the table. Excuse me. They index the table, the vector table, so the CPU knows where to go. Now there is a concept of priority in with the interrupts, where you can assign priorities to interrupts, where it turns out on the Cortex series that if you're currently in an interrupt routine, a higher priority interrupt can come in and preempt that interrupt, and they can be nested, which is kind of neat. So you can read through how the priority systems work. Now, to handle all of the internal interrupts, there is no controller. The hardware lines are inside the core. So the only place you enable the interrupts is in any peripheral. So the systic is a peripheral, and we can find the system tick timer. And in the last video, we looked at the control register. There is an interrupt or an exception request. Once you enable this, it just will fire. It'll interrupt. Now, what's special about peripheral interrupts, starting at exception or vector number 16 and above, is that all of those hardware lines, and keep in mind, these are actually, internal connections in the chip. They're logic signals. They get run through an interrupt controller that's next to the core. And in the ARM Cortex world, it's called the Nested Vectored Interrupt Controller. I call it the NVIC. And it's kind of like a peripheral. Now, it doesn't matter who makes the particular microcontroller. If it has a Cortex M0 Plus, it has an NVIC. And the registers for the NVIC, for example, the set enable, the clear enable, they exist at these absolute addresses. They exist here. So it's a constant. In the case of the M0, there's up to 32 external interrupts. There's priority levels. There's this concept of interrupt tail chaining, which I'll leave that to the viewer here to kind of read about what tail chaining is. It's actually really cool, and it improves interrupt performance on back-to-back interrupts. But if you come and look and read through this manual, everything that you want to know about the interrupt controller is here, and how to turn interrupts on. So, for example, the set enable register, if we want to enable a certain interrupt number, now this is the interrupt number, not the vector number. So, for example, IRQ starting at 0, which is exception 16, IRQ 0, they're enabled. Everything below that are either by default enabled, or once they're enabled in the core, that's it. They don't pass through the interrupt controller. So, for example, if you wanted interrupt 2 to be enabled, you set bit 2. There's this to disable interrupts, you use this register. There's a register to tell you if a set is pending or a clear is pending. And then there's these priority registers where you can set a priority for each interrupt. So that's the background at the lowest level. That's what we have. We have this interrupt controller that we have to deal with. So let me bring up the code. Now I have some example code. That first we're going to look at that systic again in our systic C. And we initialize systic. Remember, this is internal to the Cortex core. On this line here, I simply set the tick int mask. As soon as that's enabled, interrupts will be enabled from the systic in the core, and we jump to the systic handler. Now, the distinction is, for any other peripheral, there's one other step involved. You have to enable the interrupt in the peripheral and on the interrupt controller. All right. Now, as a quick review, in the last video, whenever you generate new code, in the kineticisinit.c, a vector table is generated for you. Now, it looks a little goofy, and I'll go through this once again. All this vector table is, the way it's implemented in C, is just an array of function pointers. All a function pointer is an address. So this is like a goofy way of saying we're creating a function pointer, it's constant and it's read-only, and we create an array of it called interrupt vector. The only other goofy thing to look at in the declaration of this array is we don't want this vector table anywhere, we want it in a certain place. So this will tell the linker to put it in a section called vector table, and if I look in my LD file, my linker script, we declare a memory area called interrupt starting at 0, and then the vector table gets assigned there. And you can look through the manual, you can look through GCC documentation to see you know, some of the intricacies of the linker script. But basically all that directive does, that attribute, is tell the linker, make sure that this array gets placed at address 0. That's important. So in the table, we have the initial location of the stack pointer. The next one was the reset handler, if we remember. So what happens after reset? We don't actually jump to main. Some think you don't. You go to a function called thumb startup. And thumb startup implements C startup code. And if you were really curious, you could dig and kind of find, you know, what thumb startup is. So here's thumb startup. You know, initialize some registers, some hardware, and you can kind of unwind, you know, how the C subsystem is set up. It has a 0 out RAM that's supposed to be initialized and whatnot. So from there, what the default project does, it puts in default symbols for the interrupt handlers. Now, the reason I used in my systic routine the name systic handler is that was kind of the name put in the table for the systic, you know, vector. There's kind of a, you know, trick in C that there's an attribute you can put with, you know, a function called weak. And what weak does is that it says, you know, it tells the compiler, if this function is declared anywhere else, use that function, but if not, revert to this other function. So if when the linker kind of goes through and there's no NMI handler or no DMA handler ever declared anywhere else, just insert the address, use this default handler, which just sets a breakpoint. So all interrupts have some place to go. Now, excuse me. So I just use systic handler. So you could go and put your own names in here, but there's no reason not to just use kind of their names. So at this point, let's start thinking about how we actually, you know, implement or turn on an interrupt in a peripheral. So for our example, I'm going to use the timer pulse width modulator unit. It's a fairly easy peripheral to program, and you know, it doesn't take a whole lot of work to see that it's working right. So I'm going to open up the reference manual for our Kinetis device. Now, one chapter I do want to point out to you is in the reference manual for the Kinetis, the KL25P80. There is chapter 3 is chip configuration. That's a good go-to chapter. It's kind of like a catch-all for all the stuff, you know, that if it can't fit anywhere else, it goes in there. And it talks about any implementation-specific items regarding the core, you know, the microprocessor. So there's a chapter on the interrupt vector controller, and it kind of shows you all of the modules, the peripheral going into the controller, and it says to get the real description, you go to the technical reference manual. But in here is this is where it actually fills in. It tells us, you know, what peripherals map to what vector. So you see the first 16 here are for the ARM core, then the 16, you know, 16 through 48 come after that. So they don't call, in here, they don't call it exception number, they call it vector number, maps to the table, but they don't start enumerating the IRQ number, because IRQ number is kind of the non-core vector. So what I'm going to look down through here is we see the timer pulse width modulator. They're on numbers 17, 18, 19, and the vector number is 33, 34, 35. So if we were to come back to our kineticity, we would see that, you know, 33, 34, 35, you know, that would be the kind of, you know, the number of indices into the table where our handler's at, and that's correct. So it's kind of nice that this table's already set up for us. You could certainly make your own table. Some people make their own tables in RAM because you can relocate. The vector table at reset is at 0, but it doesn't have to be. There's actually a register that you can relocate the table. So now we're going to look at, okay, so we want to demonstrate, excuse me, how to use, you know, an external interrupt, or I should say a non-core interrupt. So let's go under the timer section, and we have the timer pulse width modulators. Oh, no, that's for the configuration, I'm sorry, how they're configured. TPM. So the TPM module in this Kinetis is based upon the ones in the HC08 series, and they're pretty simple. The way I like to think of all these timers, they're simply a counter and some fancy comparators. And that's really all they are. So there's a base counter that's 16-bit that you feed it a clock source, say from the internal bus clock. It goes through some divider, prescaler, and it just counts. It can count up or down or both, but that's all it really does. Now there's these compare channels that can be used to generate PWM. That'll be for a discussion another day about how to use those. But one of the simplest interrupts to use in a TPM module is what's called the overflow interrupt. So the module counter counts from 0 to some value called mod. And when it gets to mod, that value, a flag called timer overflow flag gets set. Now, if its interrupt is enabled, it will pass out and go to the interrupt controller. It'll pass out of this gate and go. So every time this counter overflows, we can get notified of that activity. So once you set up this module counter, the clocking, and the interrupt enable, we can get interrupts. So let's look at that. So I have an example C file. I'm going to use TPM1. We could have used any TPM. Now there's some details here. I'll leave it to the viewer here to go through. But to make the TPM work, I read through the manual. The first thing we need for the TPM is a clock. So I wanted the PLL clock over 2. So what I did is I selected that. In the system's option register, there are some bits that kind of change like what clock can be routed to the TPM. Once that's done, there's actually a set of registers. Remember, all peripherals in the Kinetis, most are turned off. The option register selects which clock will get routed, but it's still, once the routing is set up, it's still not enabled. There's a clock gating register. We want to make sure whatever clock we select gets turned on. Once that happens, I blow away the configuration registers. The first thing I do is I set up the prescaler. I simply look at the prescale bits, and that's in the status and control register. Now, the other bit that's kind of important is the overflow enable. So let's look at the status and control register. And the first thing, remember, I set was the prescale, the divider, divided down and then this overflow. So once this bit is set, every time the counter overflows, this timer overflow flag right here will be set. Now notice what it says here. The timer overflow bit is cleared by writing a 1 to the timer overflow. That's going to be important. We're going to see that. We're going to see that later. So this flag is available, and we do have to reset it. Now the mod value is something we got to set. The counter counts from 0 to something, and we want to count to some predetermined value. Now you notice here I have a goofy formula. All of this formula, based upon my prescaler, my clock source, and my overflow frequency, it kind of figures it out. So you can work that equation out. So I knew my clock, my prescaler, and I wanted a 50 hertz overflow frequency. That's every 20 milliseconds. You know, I figured out that calculates the mod value to put in here. Now keep in mind there's all kinds of divides in here, but because all these values are constant, this is evaluated at compile time, not at runtime. So once we set up the mod, everything's good to go, but we have to enable the counter. So there is a bit to tell the counter to go, and at this point, it's going to go. One last step. We have enabled the interrupt within the module, but we have not enabled the interrupt in the NVIC, the Nested Interrupt Vector Controller. If we wanted to, we could open up the technical reference manual, and we could come in here and look at this set register and find our IRQ number and set the bit. Now, in the Kinetis sample code, there's a nice sample bare metal sample code package, and let me open it up for you. It's called KL25SC Rev 5. If you just go to, say, any of the Kinetis devices web pages or the Freedom web pages, you can get to it. Here, I'll actually just show you. I'm bringing it up on a web browser. Just give me 1 second. So if I come under downloads on the Freedom Board page, this KL25SC, this has some sample code. For a lot of it's processor expert, but there's a lot of drivers that I pull things out of. I tell students there are tools like Processor Expert that auto-generate code to do a lot of this, but it's good to always learn how to do it yourself, because that way if Processor Expert doesn't work or you don't have it, you're not dead in the water. So in the bare metal, under source, there's all kinds of neat stuff. Well, under the CPU, there's a file called armcm0, and all it is some low-level code for setting the bits in these registers. So let's take a look at CM0 and what's in there. You know, I have a function that can stop the processor, put it in the wait, but there is a function called enable IRQ. And this is where you tell it which IRQ number, not vector number, IRQ number you want enabled. And so I put a note in here. We're going to see this. If you use the interrupt vector definitions from the header, the Kinetis header files, you got to subtract 16 to get rid of the ones for the core. But you notice all it does here is use the interrupt set, register and mux the clear register. You could have done that on your own, but there's a nice function for it. So if we look in the TPM1, I use this function enable IRQ. Now if I dig up, let me go back to the reference manual. And I find the interrupt controller TPM1. TPM1, its vector number is 34. That's the table entry, but the IRQ number, because we don't count the first 16, is the number 18. So I could have just went in here and typed 18. But one thing, the Kinetis header files, they don't give us the interrupt numbers, the IRQ numbers, but they have a nice table of the vector numbers, so they include the first 16. So what I did is I just used this enumeration and just subtracted 16. You could make your own table, or you can modify this IRQ. You could say enable vector and do the subtraction in the code. It doesn't matter, but that's why we subtract 16 there, just to use that function. But you could certainly write your own. So the only other piece we need is we have to make sure we have a handler function. So I have one called FTM1 Handler, IRQ Handler, and the reason I called it that is because that was the default name that was put in the table. We can change it, but there's no reason to. Now, so whenever this, every 20 milliseconds, when this overflow interrupt fires, the CPU is going to jump to here. Now, here's one thing that's really important, is that some peripherals, simply having the interrupt service or reading maybe its results register will clear the interrupt. In the case of the timer, the TPM timer, the overflow mask, you have to manually clear it, or else as soon as you leave this interrupt, it'll come right back, because the interrupt will still be raised to the controller. So what we do is we see if it's set, and then remember to clear it. It's set in the manual. You clear it by writing a 1. So once we do that, we've cleared this interrupt condition. I have a variable called TPM1 ticker. It's just a ticker that ticks up every 20 milliseconds. If it's less than its max value, increment by 1, and that's it. So it works kind of like how I did the sysTick in the last example. So in my main routine, here's what I did. I initialized the PLL. I have an init freedom function that initializes GPIO for the lights. I turned on the sysTick just so you can still see that working. I initialize the TPM. Then I just have a for loop that checks to see if the ticker is greater than 50, equal or greater. If it is, remember, since the ticker goes every 20 milliseconds, 50 ticks is 1 second. I toggle the red LED. So what I'll do, just to show you that this works, I'm going to download this code. And we'll give that a minute. Give it a minute to think. Okay, boy, that was weird. Let me try this again. Actually, I just moved this project, so when all else fails, do project. Let's do a clean. Terminate and clean. I copied the project location over, and I didn't do a rebuild, so it might get a little confused. Okay, let's try one more time. All right, it's happier now. All right, so before I press go, what I'm going to do is I'm going to come over here and just put a breakpoint. So if we did everything right, which we did, there we go. We get this nice interrupt. So what I'm going to do is I'm going to let it run. I have a camera pointing towards my board. There's the LED going in a second. All right, so we know the interrupt's working. Now, this video I've said a lot, but what I want you to take away, we really didn't have to do much more to our function in a, to turn on the interrupt. Remember, it's a two-step process. You have to enable the peripherals interrupt, then simply enable it on the interrupt controller, so the interrupt controller sees it. Once you do that, as long as you have an interrupt vector table entry, you're good to go. So the other interesting thing is if you ever run into an issue where, and I'll do a quick demo, where you forgot to actually put in the handler name or you typed it in wrong. Because we had those weak symbols that had an alias for those functions, the machine does have deterministic behavior. So let's see what happens. So I took the handler out. Let's see what it does. Let's go run. It jumps to the default handler and throws a breakpoint. That's a way of telling you that you have an unhandled interrupt. So that's useful to know. So let me go back here and remember to change all this back. So I hope that's a good introduction. So at this point, you know how to enable core interrupts. The systic, we saw an example of how we do an interrupt outside the core. It's actually pretty simple. It's just one extra line. And you can go ahead and start using interrupts with other peripherals. You don't have at it.